Hello everyone. Welcome to today's live broadcast, a thermoelectric cooling approach to SWIR spectroscopy with InGaAs array detectors. I'm Laura Bush, Editor-in-Chief of Spectroscopy, and I'll be your host today. We're delighted to bring you this educational web seminar presented by Spectroscopy and sponsored by Andor Technology. Andor's high-performance modular spectroscopy solutions encompass a wide range of market-leading ultra-sensitive CCD, ICCD, and EMCCD detectors, as well as a comprehensive range of research-grade spectrograph platforms and comprehensive control software solutions. Andor products assist leading researchers in achieving high-quality results and breakthrough discoveries through techniques such as LIBS, Raman, and fluorescence spectroscopy, while also offering highly sensitive yet rugged detection solutions for challenging industrial applications. We have a few important announcements before we begin. First, this webcast is designed to be interactive, so we encourage you to ask questions during the event. You can type your questions in the Q&A box located to the left of the presentation window. You can enlarge the slides at any time by clicking the Enlarge Slides button, which is below the presentation window, and the slides will advance automatically during the event. And if you have any technical problems viewing or hearing the presentation, just click the Help button below the presentation window. And lastly, at the close of the program, we will ask for your feedback. We hope you'll complete that short survey because your responses will help us shape the programs of future webcasts. I'd now like to introduce today's speaker. We're pleased to be joined today by Antoine Varagna, a product specialist at Andor Technology, where he has worked for more than 10 years. Antoine is currently responsible for the development strategy and marketing of the company's spectroscopy and time-resolved detection solutions. Previously, he held positions as a senior optical engineer and project manager in charge of the development of various spectroscopy systems, including spectral instruments and gated detectors. He has a master's in plasma physics from l'École supérieure des procédés optiques et électroniques at the University of Orléans, France. Well, thank you for joining us, Antoine.
Thank you.
Yes.
Okay. Thank you very much. Thank you, Laura. So my name is Antoine Varagna, and today we're going to talk a little bit about the Thermo-Electric approach to shortwave infrared detection, and particularly focusing on the detector side, which are InGaAs array detectors, and more specifically the detector sensitive to 1.7 micron. So just to give you a little view on the agenda, we're going to look at first some fundamental aspects of sensitivity for detector, and especially the signal-to-noise ratio, SNR considerations. Then I will focus on the actual effect of cooling for this infrared detector, this InGaAs sensor, and the effect on performance, how performance can be tuned or how it evolves with cooling the sensors. I'll spend a little bit of time then on the is cooler really better for InGaAs sensor detector, which is generally a perception people have in using this type of detectors. And then I'm going to look at the performance and the pros and cons between liquid nitrogen-based cooling and thermoelectric cooling for this type of detectors. And then we'll conclude and have and take a few questions at the end of this webinar. Okay, so sensitivity is defined as a signal-to-noise ratio, and it's typically proportional to the signal over the square root of the noise. And these can be detailed as so. So the signal is just proportional to the number of incident photons on the detector and the quantum efficiency, QE, of this detector. The dark noise, which is something I will focus a lot on in the next slides, is a temperature and time dependent thermal noise from the detector and its surroundings. The short noise is just the statistical incoming photon variation on the sensor. It's basically the ultimate sensitivity limit to any detector, any pixelized detector. Spurious charge is an effect of impact ionization when actually charge are transferred onto the sensor matrix from pixel to pixel to be read out. And then finally the readout noise, which is basically the digitization noise, transforming the signal from a detector into a computerizable signal. Taking the same equation, I will focus especially on the dark noise, which is the quantity I've highlighted here. And for those who are familiar with visible CCD, the dark noise is typically the sensor dark current that builds up during exposure times. For InGaAs detection with sensitivity in the near infrared beyond 1 micron, there's actually an extra element to it, which is called the seen black body emission, which is not related to the sensor itself, which is related to the seen by the sensor itself. Okay, so if you look at an example of a sensor package for a CCD, for example, I've just put a picture of one of Andor's CCD on the left called an InGaAs, and the sensor is sitting just behind the window as highlighted. The sensor is seeing a number of black body radiation sources. The first one will be the sensor housing and sensor enclosure black body radiation, which is sitting roughly at room temperature. And that includes the entrance window. And the second source of the black body radiation is actually, if you couple this type of detector to spectrograph, it's actually the black body radiation from the optics inside the spectrograph. For example, the focusing mirror inside this spectrograph. So typically black body and its effects is associated to be further in the infrared. So here on the left, I've represented a typical black body profile, which follows the Planck equations. And basically, I've represented that at room temperature, typical laboratory temperature, which is about 293 kelvins. And I've looked at it in the 600 to 1700 nanometer region, which is where the sensors we're going to look at are sensitive. So the curve on the left shows the black body radiation at this room temperature, which peaks at 13 micron and extends from up to 60 micrometer. But if I look at the part in what interests us, which is overlapping with a sensor quantum efficiency, which I've represented here, the left axis is actually log scale, which is why the curve is going like that. So I'm overlapping the sensor quantum efficiency and the black body emission of the room temperature elements. Elements are room temperature if you want. And if you look at the axis on the left, the number of photons emitted by this black body radiation at this temperature, it's far from being negligible. Here we consider the black body emission of, say, a point source. So it's actually the radiation at 360 degrees or around this point source. But still, you're talking about 10 to 16 photons emitted per this element area. So one of the key challenges theoretically is to assess how many photons are seen by 1 pixel of a detector from this curve. And it's very hard because the vacuum chamber in which the sensor is sitting has a complex geometry. So instead of theoretically guessing how many photons, background photons, dark noise photons will be seen, we're actually measuring the dark noise in reality with a sensor. So how do you measure dark noise with an InGaAs camera? Typically, you would put a blanking plate in front of a detector and take a long exposure and look at the dark noise there. But with InGaAs detectors, the blanking plate in front of a sensor will also emit black body radiation. So what I've represented here is the dark noise with different scene temperature. So you're basically circulating a coolant behind the sensor and as well in front of the sensor. So the blanking plate sees this 30 degree, 20 degree, or 10 degree scene. And you can see the steps and the shape of the curves here with the sensor cooling temperature, the actual sensor cooling, which can here go down to -90. So you can see that between a 30 degree scene and a 20 degree scene, which is ambient temperature, which is typically what you have with a spectrograph when the camera is attached to a spectrograph, you can see quite a huge difference, a huge step, and that's typically the representation of your black body radiation. Because when you go to this lower sensor temperature, the sensor dark noise becomes much lower than the black body radiation. So the further you cool the sensor, the more the black body radiation become predominant, and that's not something you can cool away unless you circulate this water. So typically the dark noise as seen here at say between -70 to -90 plateaus, and it's pretty much your black body radiation. So you're talking tens of thousands of electrons per pixel per second, which is far from negligible. Just to give you a little idea on the signal to noise ratio and how the different values in this signal to noise ratio pan out. The clocking induced discharge is typically very, very small, so we're going to ignore that in the current view. Your shot noise is proportional to the square root of your photon, so the more light you have, the more shot noise you're going to have. That's very simple. The readout noise with this type of detectors in the order of few hundreds to a few thousands of electrons, depending on which mode you're running. HS stands for high sensitivity, and HDR stands for high dynamic range. If you now look at the dark noise, and basically I've plotted the sensor temperature on the left from say the -70 to -110, which is typically liquid nitrogen cooled temperature used for this type of detectors, not the liquid nitrogen cooled temperature that you would have typically, which would be much lower than that. And I've plotted that against the sensor exposure time from 1 second to 4 hours, and you can see the amount of dark noise that's building up, which is much greater than any other noise in the CCD. So typically you can say that the InGaAs sensors, InGaAs cameras sensitivity is dark noise and shot noise limited. Now I'd like to point out something. If you're cooling your sensor to -110 degrees, for example, and you're doing extended, say 4-hour sensor exposures, you're actually accumulating nearly 160 mega electrons of noise on your CCD. And you have to keep in mind that your pixel well depth is only about 170 mega electrons, so you got very little space from your well depth to actually see your signal. So you're still accumulating quite a lot of noise, of this dark noise. Now, I've plotted 3 graphs on the 3 next slides, looking at the signal to noise ratio for different photon fluxes. Here, 1 photon per second, which is extremely low photon flux. And I've plotted the signal to noise ratio versus the exposure time. Now, in order to have a meaningful signal, the signal to noise ratio has to be above 1, which is typically the dotted line I've shown on the graph. And I've highlighted the crossover points of the different curves for a signal to noise ratio of 1. And then I looked at different sensor cooling temperature from -10 to -120. So -10 is the curve at the very bottom, which gives you basically a signal-to-noise ratio which will always be below 1. So you never get a useful signal at that cooling temperature with that photon flux. If you keep on cooling the sensor, you can see the cluster at the top of lines, and it's basically between -70 and say -120. You have extremely little differences between the signal-to-noise ratio. So you can cool your sensor as much as you want. You have very little gain according to this graph. And between a sensor temperature of -70 and a sensor temperature of -120, there's only a difference of 1 minute to achieve a signal-to-noise ratio of 1 minute exposure time. So very little, knowing that you've already accumulated for say 15,000 seconds. That's pretty small. So even at low photon flux here, we can see that cooling the sensor beyond -70, -80, -90 doesn't make such a great difference in terms of exposure time, in terms of signal-to-noise performance. I move to the next slide, and it's typically the same type of representation, but now the photon flux is about 100 photons per second, which is still quite low light. And you can see that between a sensor temperature of -70 degree and a sensor temperature of -120 degree, it takes less than 1 second extra in terms of exposure time to achieve a signal-to-noise ratio of 1. And again, if you look at the part circled in blue on the graph, you have very little difference between -70 and -120 degree curves. Very little advantage to go beyond the -70. Just one point here, for a signal-to-noise ratio of 1 here, the minimum of photon detectable at -70 degrees is actually around 800 photons. Now if you move to photon fluxes of much greater, here 10,000 photons per second, you can see the curves very much overlaps, and you can actually see that -50 degree sensor cooling temperature is more than enough to achieve the very similar signal-to-noise ratio compared to say a -120. So the key message here is that over a wide range of photon fluxes, photon emitted by your sample, there is very limited additional advantage in terms of performance, in terms of sensitivity, to go much beyond the likes of -70 or -80 degree. Going to -120 will get you maybe a slight extra signal-to-noise ratio, but at the end of the day, the gain is really minimal. There's another aspect that's very important to understand when looking at any near-infrared sensors, whether it's a CCD deep depletion or it's an InGaAs. When you cool down the sensor, the quantum efficiency in the longer wavelengths actually drops. So here these graphs represent a spectrum of a broadband tungsten source. And basically with exactly the same exposure time, which is here 100 accumulation of 1 millisecond exposure. And we look at the signal seen by the sensor, and then we cool the sensor. So typically from 0 degree, that would be your curve on your right, the purple one, to -85 degree, the curve of the blue, and then the dotted line in the -120 degree, where historically sensors have been operated with liquid nitrogen cool. And you can see that the cutoff moves quite a lot. You're losing a lot of QE in this region. If you're taking the difference at 1625 nanometer, if you're looking at the intensity drop between 0 degree cooling and -80 degree cooling, you're losing 96% of your quantum efficiency effectively. So if you're working in this region, it's very important to understand that the more you're going to cool the sensor, the more quantum efficiency, the less sensitivity you're going to have. Here I've plotted a very quick, very simple experiment that's taken with one of our customer, Professor Wesley Brown at the University of Groningen, and basically using an Andor InGaAs detector and looking at the transmittance of a Pentane compound in the 1600 to 1700 nanometer region, and looking at the first overtone of a CH stretch here, which is about 3000 centimeter minus 1. And you can see that at identical exposure times, the absorption, the peak, the dip here you can see, which is more important that the lower temperature just tends to completely collapse and disappear the more you cool, because the quantum efficiency of the sensor is pretty much gone, completely gone, and you can see quite a lot of noise on these curves at lower temperatures as well. So just this example to illustrate physically what can happen if you're working in the 1600 to 1700 nanometer region with this type of sensors. Now just a little focus on actual T cooling platform, so Thermo-Electrically cooled platform. So typically your sensor is in a vacuum environment. The vacuum environment is basically to remove any moisture from the air that could contaminate the sensor, that could degrade the sensor with time, or that could facilitate creation of vapors on the sensor. And then these sensors are typically placed on this little pyramid shape here called the Thermo-Electric Peltier cooler, which basically extracts the heat from the sensor and sends it to a copper block that you can see at the back, and you have actually water pipes in this copper block, so you can flush away from the detector the heat as such, and as well use a fan to remove it, to take away the heat from the detector head. So in liquid nitrogen configuration, there is no thermoelectric cooling here. At the back of this copper block, if you want, you have the dowel that holds the liquid nitrogen, and typically the liquid nitrogen is not operated. The sensor doesn't see the temperature of a liquid nitrogen, because typically manufacturer would heat up this copper block, or this block on which the sensor would be, to work at temperature between minus 120 and say minus 50 degrees. So is cooler necessarily better in terms of performance? We've seen that the dark current improvement beyond say minus 80, minus 90 degrees is extremely limited. The signal to noise ratio in the low photon regime show a very little improvement when you go beyond minus 70 degrees. And you could see that all the curves were overlapping when I plotted the signal to noise ratio versus the exposure time. One thing to notice as well is over the last few years, liquid nitrogen cooled camera manufacturers integrate this heating system just behind the sensor, so the sensor can actually be operated more likely in the minus 50 degree or minus 100 degree, because researchers realize that there's no need to go beyond this point for the vast majority of their experiments. The other thing with liquid nitrogen is that, as I said, you're heating up the substrate on the interface on which the sensor is integrated. So you're basically actively heating the environment of the sensor, fighting the active cooling of a liquid nitrogen, and as well fighting the natural ambient heating. So the big challenge when you're working with liquid nitrogen cooled cameras is to get a good sensor temperature stability. that's completely different from the temperature monitoring. What's actually the real temperature at the sensor, which is hard to stabilize. And also, as we've seen, the quantum efficiency in the 1.6 to 1.7 micron region means that the best signal-to-noise ratio may not be at the lowest temperature, far from it, because of this quantum efficiency drop. So why using thermoelectric cooling for low-light short-wave infrared spectroscopy? Well, first of all, the signal-to-noise are very comparable to the ones achieved with liquid nitrogen-cooled cameras, even at minus 120 degrees. One of the advantages of a thermoelectric cooled camera is that you can use water to flush away the heat from the sensor head, and you can actually cool the head. So normally the head would be sitting at the room temperature, but if you're using a 10-degree water coolant through the detector, your body will start to sit at 10 degree lower, compared to the ambient. And then you've seen the difference in terms of dark noise that it makes. So that's a very attractive architecture in that regard. The second thing is, for some people it's not a problem. For people where experiments are integrated in massive optical tables where access to the detection system is quite tricky, or then thermoelectric cooled cameras don't need any handling of liquid nitrogen, obviously, but are very much self-contained. You can basically have a water chiller sitting beside the camera that would always provide the same level of cooling performance regardless, and over an extended period. You don't have to fill your dewar every few hours when it comes to liquid nitrogen cooled cameras. As I said as well, the better temperature stability, because in liquid nitrogen cameras you're fighting the active liquid nitrogen cooling with active heating of the temperature environment. Transportability, basically if you don't have to refill your dewar with liquid nitrogen, with thermoelectric cooled camera you can just have a little recycler, so your cooling environment is very much self-contained, and you can basically integrate these instruments, this type of detectors, onto transportable instrumentation or onto some more industrial environments without having to interfere with the cooling system or maintain the cooling system performance. I'll put down below as well, there's actually some cost associated to using liquid nitrogen. And that's an example scenario for liquid nitrogen cost over a few years. So if you're taking in account a typical consumption and a typical requirement per year, which is here arbitrary setup, 400 liters of liquid nitrogen, and you're working out the cost involved with renting the dewar or to store the liquid nitrogen, the cost of liquid nitrogen, which can feel fairly small, and then everything adds up, and over a period of 5 years you can still spend nearly $15,000 or 10,000 euros, which is an additional cost that people have to keep in mind with this type of camera. So now I've pretty much finished with the technical aspect of it. I'd like to spend the next few minutes looking at actual applications, actual measurements from some of our customers using our cameras. And I'll go over about 3 or 4 different applications, look at the different scenarios, look at the different setup of a camera to achieve the different results. And the first one is looking at, it's very basic. It's 1064 nanometer Raman Spectroscopy, and basically looking at 3 different compounds. The one on the top, the acetonitrile toluene, so basically in a cell in liquid form, and then a couple of next samples, which are actually solid samples. And you can see the type of exposure time used with these. So this data was taken with an Andor IDAS InGaAs array, cooled at -60 degrees on a 8-meter spectrograph. And that was done by Professor Wesley Brown at University of Groningen. So you can see with laser powers of between 20 and 200 milliwatts, and using a few exposure times of a few seconds, you get very, very decent spectrum here. Obviously, you're working in the infrared, so they're not necessarily the resolution is not as good as you would have in the visible, obviously, but you can still have very, very, very clean spectrum after a few seconds, and then not using a very deep cooling. The second one is an other aspect of 1064 nanometer Raman spectroscopy, but this time looking at catalysis kinetics. So again, using a very, very similar setup with an Andor IDAS InGaAs, -60 degree cooling, small spectrograph, a 200 milliwatts laser, and again, the similar setup at University of Groningen, and basically looking at the catalysis and the conversion rate of the reaction shown in the top right of the screen here, and basically looking at the CEC carbon line highlighted on the right of the graph, ratio to the aromatic breathing mode, which is highlighted here as well. And this ratio is plotted on the graph on the left, which shows the conversion monitoring and basically the consumption of the first product over time. And that's looking at the 1625 centimeter -1 CEC carbon-carbon bond. So here the 6 accumulation of 5-second exposure. So with 30-second exposure, you get very, very decent spectrum, and you can actually clearly see the kinetics taking place, seeing the different levels of intensity of the carbon-carbon bond. Now the next application is a micro-photoluminescence spectroscopy. So one of our customers in Spain at University of Madrid and University of Valencia use again the Andor InGaAs 1.7 detector, and with 10 to 100 second exposure, and I believe some around -80 degree cooling, thermo-electric cooling, did photoluminescence of quantum nanowires, and looking at the photoluminescence in blue on the graph on the left is the photoluminescence which is typical of the insulating excitonic gas, and then on the red is a metal-like electron hole liquid photoluminescence, and you can see the variation of this photoluminescence with excitation power through microwatts to a few hundreds of microwatts. So again, with 10 100 second exposure, weak enough photoluminescence could be acquired. The next application, also monitored at University of Groningen by Professor Wesley Brown, is Singlet oxygen spectroscopy. So Singlet oxygen spectroscopy are basically used to look at some reaction, some photooxidization reaction and degradation of organic material, and basically the reactive intermediate in these is singlet oxygen, which is most often produced by sensitization. That means by energy transfer from a electronically excited sensitizer molecule to molecular oxygen. So here, looking at the peak, at signal peak at 1275 nanometer, which is a typical emission of the singlet oxygen wavelength, and basically bringing down the exposure time, as you can see on the right, you get quite a clear view of the signal still. So here the sensor is again cooled at minus 60 degrees and the power of the laser about 300 milliwatts. So the exposure time are extremely short, and even with a 10 millisecond, you can still have a fairly decent signal to analyze. So that concludes my presentation. So basically, just this webinar is really about making people aware of the different aspects of cooling an in-gas detector. And the thing I really want people to take away from this webinar is the fact that historically, liquid nitrogen has been the platform of choice for cooling this type of sensors. When looking into details on the actual performance versus cooling temperature of these devices, it's clear that temperature of say minus 80, minus 70 degrees are actually very sufficient for the vast majority of experiments, even at low light, at low photon flux. The second aspect of this webinar is the quantum efficiency drop in the longer wavelength for this type of sensor, which is very important to keep in mind when working in these regions. The third one is taking away the convenience of the Thermo-Electric cooling, the basically self-containment of the cooling interface without having to service this cooling interface regularly. It can work year after year without any maintenance. So that's it. Thank you very much for your attention. I'll now be taking questions.
Excellent. Thank you so much, Antoine. So yes, as Antoine said, it's now time for our question session. And again, you can submit questions using the question function that is right to the left of your screen, the Q&A box, excuse me. Okay, so let's get started with the questions. Okay, so the first one is, can the T detectors, thermoelectrically cooled, detectors, be used to femtosecond time-resolved IR measurements? And if so, what specific camera do you recommend for this type of time-resolved applications?
So typically, in-gas detectors have a vertical shift speed which is in the order of microseconds. So they are PDA, so they are one line. So your actual time resolution for these between frame is actually of the microsecond level.
Okay, very good. Sorry, we can add more to that?
Yeah, just a couple of points. If you want to work into shorter, I'd say, windows in terms of time, there are photocathodes on ICCDs that exist that can go up to a micron, which is not quite as far as these in-gas PDAs, if you want, but you get time resolution of nanosecond scale.
Excellent. Next question, how does IGA compare with CCD at 1064 nanometers?
Sorry, I'm not sure about the IGA, what it does stand for, so I take this question outside and reply. Okay.
Very good. Next one, how long can we go with the thermoelectric cooling systems? Oh, how low can we go?
Okay, so thermoelectric cooling systems can work in two modes, just air-cooled. So typically with air-cooled, you reach minus 60, minus 70 degree. If you as well add water cooling to the camera, say 10 degree water, you can go down to minus 90 degree. Now, when you use lower coolant temperatures, you have to be very careful of a dew point in your room. The dew point is basically when you start to have condensation on the optical interface you're cooling, because the humidity in your room can be too high. So you have to be very careful about that.
Okay, very good. And so that person who asked the question about the previous one said that by IGA they meant in-gas array. So the question was, how does in-gas array compare with CCD at 1064 nanometers?
At 1064, so the CCDs actually the band gap of silicon cuts very, very close to 1064, actually just about 1100 nanometers. So the quantum efficiency of these devices is very low CCD-wise, and typically they have very, very high dark current as well, so you need to cool the sensors, these deep depletion sensors, and because you cool these deep depletion sensors, same effect than on the InGaAs, you lose even further QE, quantum efficiency. So effectively at 1000 nanometer you have very, very low quantum efficiency compared to the InGaAs. So if you actually do signal to noise ratio measurements, or even theoretically, you'll find that the InGaAs is still better than the deep depletion at 1064.
Excellent. And someone was asking a technical question about the instrumentation. Does the sensor have a window?
The sensor itself doesn't have a window, but the vacuum enclosure in which the sensor is has a window indeed, which is optimized for the near infrared. So as I said, in order to cool your sensor and not have degradation of the performance of the quantum efficiency or actually create condensation of the sensor actually sits in a vacuum or a backfilled environment. So there's no window directly on the sensor. There's a window in front on the vacuum chamber.
Excellent. And one more technical question of something you were presenting. What is NCIC?
Okay, so N stands for the noise. CIC stands for clocking induced discharge. So if you imagine a CCD matrix, which is made of all these little pixels, the signal is basically read by clocking electrons from each pixel down towards a readout register. And by using this clock, by moving these electrons, you can sometimes create electrons noise in this process by impact ionization. So this has very, very low probability. This is not really important for CCDs, but when you move to technology like EMCCD, electron-multiplying CCD, where you have an amplification chain on the sensor itself, then this clocking-induced discharge can be amplified 1,000 times. And this clocking-induced discharge becomes the limiting factor for the sensitivity of this electron-multiplied CCD. So it's a noise to be aware of. It exists in InGaAs arrays, it exists in CCDs, but in these two types of detectors, it's extremely low compared to any other noise. So you can't even see it. It's buried into any other, all the other noises of the sensor.
Excellent. And I think we'll just do one last question, which is you talked about the different advantages, one of them being convenience. Do you see this being adopted in particular for certain types of work or for certain types of researchers? Yeah.
So well, we do work with two type of customers, with two type of users. So basically, people using, for example, Raman microscopes, were sitting in industrial environments or sitting in process control environments, where access to these machines is very limited. So the advantage of not having to refill liquid nitrogen to the camera is a certain advantage. In terms of application, industrial application would probably benefit the most, but people that have complex experiments that can't have a very easy access to liquid nitrogen, where the experiment is embedded into a bigger systems and is going to be traveling around. That's typically the type of setups where the Thermo-Electric cooling platform would be of advantage. And as well, you can see that the performance is very, very, very close to liquid nitrogen type cameras. So at the end of the day, you have minimum gain in terms of performance between at these lower temperatures.
Excellent. Well, thank you so much, Antoine. So I'd like to wrap up now. So I'd like to thank the audience for your interesting questions and your participation in today's event. And I'd like to extend our thanks to our sponsor, Andor Technology, for making today's educational webcast possible. Please note that this webcast will be available for on-demand viewing through September of next year. And you'll receive an email from Spectroscopy alerting you when the webcast is available for replay. We ask that you forward that announcement to your colleagues who may have missed today's live event. We'll see you next time. Goodbye.